Hello everyone, my name is Olusegun Inetianbor. You can call me Segun. I'm an electrical engineer, a data science enthusiast, and I'm volunteering with Statistics Without Borders. So in this video session, under the subject of biostatistics, we'll be discussing the normal distribution. And this is our agenda for this module. The first subtopic will be getting an introduction to the normal distribution. And the second subtopic will discuss characteristics of a normal distribution. The third subtopic talks about the standard normal distribution. It's a variant of the normal distribution. The fourth, we talk about the Z-table and its application. And the fifth, we discuss exercises. And then finally, we summarize the model. So let's start off with the introduction to the normal distribution. There is a reason the normal distribution is called normal. Its presence can be felt throughout data science and machine learning, as well as in a variety of unexpected real-world scenarios. The presence of this distribution ranges from the distribution of heights and weights to the volume of milk collected from cows to SAT scores. It is also called Gaussian distribution. But while history has given Gauss the naming right, it was Pierre-Simon Laplace, who, building from Gauss's work, formulated the central limit theorem. The CLT is a key statistical concept that states that the sampling distribution of the sample means approaches a normal distribution as the sample size gets larger, no matter what the shape of the population distribution is. This fact holds especially true for sample sizes over 30. All this is saying is that as you take more samples, especially large ones, your graph of the sample means will look more like a normal distribution, or as you call it, a bell curve. I take it again. As you take more samples, especially large ones, your graph of the sample means will start to look more like a normal distribution or a bell curve. This concept allows for the seemingly omnipresent nature of normal distribution in everyday life. So many aspects of everyday life can be modeled by a normal distribution for this simple concept. Now, this is an pictorial description of the central limit theorem. We can see that there are so many plots with different shapes. Yeah, there are 4 different plots with different shapes. But they all end up being described by normal distribution as the sample size becomes larger. This image supports or takes more emphasis on what we just discussed regarding the central limit theorem. As seen in the illustration, various independent factors influence a particular trait. When all these independent factors contribute to a phenomenon, the normalized sum tends to result in a Gaussian distribution. Now we define a normal distribution. The normal distribution is a probability distribution that is symmetric about the mean, showing that values near the mean are more frequent in occurrence than data far from the mean. In graph form, normal distribution will appear as a bell curve. This formula here describes the probability density function for a normal distribution. Looking at this formula, we can see our mean, our standard deviation, I, and what we can call E, or Euler's number, which is 2.71828. Both pi and E, as we know, are constants. And when we put them in all these formulas for a particular data, they can describe the probability density function of that normal distribution. But we can see that since these 4 parameters, 2 are already constants, That means a probability density function for a normal distribution can be determined mainly by two parameters, the mean and the variance. The further a data point is from the mean, the less likely it is to obtain a more extreme value. Here it shows 4 different plots of a normal distribution, and their shape changes based on the parameters mean and variance, or by extension standard deviation. You can see the plots and their parameters in the top right corner of the graph. So depending on the mean or standard deviation, just by adjusting them, the shape of a normal distribution plot can drastically change. Many biological variables use the normal distribution quite well. Variables such as intelligence, height, and blood pressure naturally follow the normal distribution. For example, if you took the height of 122-year-old women and created a histogram by plotting height on the x-axis and the frequency at which of each of the heights occurred on the y-axis, the vertical axis, you get a symmetrical bell-shaped curve. So here we've properly defined what a normal distribution looks like and the parameters that fully describe it. With the normal distribution now clearly defined, we go on to discuss characteristics of a normal distribution. The normal distribution has several characteristics that make it very useful. They are as follows. 1, symmetric around the mean. When we say symmetry, or we say something is symmetric, it means that it is even on both sides. Both sides of it are equal. So in the case of a distribution, we are saying both sides of the distribution are evenly distributed. Let's put it that way. The values or data points in the distribution plots are evenly distributed on both sides of the distribution. But in this case, we're saying it is symmetric around the mean, meaning that it is evenly distributed on both sides with the mean at its center. Half the values fall below the mean and half fall above the mean. So it is symmetric about the mean. That's one of the characteristics of a normal distribution. Second is that the mean, median, and mode are equal. This makes sense considering that normal distribution, the mean value has the highest frequency of occurrence. So it makes sense that the mean, median, and mode are all equal. The area under the curve is equal to 1. The area under the curve graphically represents probability. So the total area under the curve is always 1, or in percentages, we can say 100%. And then it follows the empirical rule, which we call the 68, 95, 99.7 rule. So you will get the hang of those values, 68, 95, 99.7 rule. The empirical rule in statistics allows researchers to determine the proportion of values that fall within certain distances from the mean. The proportion of values that fall within certain distances from the mean. The empirical rule is often referred to as the 3 sigma rule, or the 68, 95, 99.7 rule. Let's try to get a better understanding of these rules in the next slide. Looking at this graph, we see here what percentage of the distribution is covered by 68. So here, looking at the graph, we can see that one standard deviation from the mean covers 68% of values. Then 95% of values fall within 2 standard deviations of the mean, while 99.7% values fall within 3 standard deviations from the mean. Around 68% of values are within 1 standard deviation from the mean. Around 95% of values are within 2 standard deviations from the mean. And around 99.7% of values are within 3 standard deviations of the mean. You can see as you represent the graph, here is the dead center of the distribution, the mean. Then the mean plus 1 standard deviation on both sides of it represents where we find 68% of values, around 68% of values. Then if we go from the mean again, we go 2 standard deviations on both sides, we find 95.44 values of the percent of the values within that range. Then if you go from the mean, 3 standard deviations from the mean, 99.7% of values are within that range. That's what the empirical rule tells us. We have clearly understood, and then we now discuss a variant of the normal distribution, the standard normal distribution. The standard normal distribution, also called the Z distribution, is a special normal distribution where the mean is 0 and the standard deviation is 1. The mean is 0 and the standard deviation is 1. Here we have a graph that also describes that. See, the mean value here is 0 at the center of the plot, and the standard deviation is 1, such that the divisions are 1, 2, and 3 in that order. As shown in the graph, the mean distribution is 0, while standard deviation is 1, and this value increments the further we go from the mean. As we see here, increments by 1, 2, 3, and so on. I think that's very clear. Take to the point, the mean is 0, standard deviation is 1. That's how a standard normal distribution works. And that knowledge introduces us to what we call the Z-score. While individual observations of the normal distribution are referred to as X, individual observations in the normal distribution are referred to as X. They are referred to as Z-scores in the Z distribution. Every normal distribution can be converted to the standard normal distribution by turning the individual values into Z-scores. Z-scores tell you how many standard deviations away from the mean each value lies. Z-scores tell you how many standard deviations away from the mean each value lies. You only need to know the mean and the standard deviation of your distribution to find the Z-score of a value. And that is quite elucidated well in this formula. The formula to determine the Z-score of a value is here, it says Z, which is Z-score, equals to X, which is the individual observation, minus the mean over the standard deviation. Yeah, I hope I get my pronunciation correctly, but this mean, they currently call it mu, while I think this one is called rho, is Latin Greek, if I'm not mistaken. So X minus the mean over the standard deviation will give you the Z-score for any individual value in a normal distribution. Note that the Z-score uses the population standard deviation, not the sample estimate of the standard deviation. If you don't know the standard deviation of the population, this statistics becomes a T distribution. Note that the Z-score uses the population standard deviation, not the sample estimate of the standard deviation. So now we discuss the Z-table and its application. We will get the thorough application of the Z-table. But let's understand what the Z-table is all about. A Z-table, also called the standard normal table, is a mathematical table that allows us to know the percentages of values below a Z-score. The percentage of values below or to the left of a Z-score in a standard normal distribution. So how do we read a Z-table? Assume that in normal distribution, for a given variable or individual data point or value, we have a Z-score of 0.21. Remember, to compute the Z-score is the individual value X minus the mean divided by standard deviation. So we have a Z-score of 0.1, for example. How do we obtain the probability on the Z-table? There's a picture here that describes what you could find on the Z-table. With a Z-score of 0.21, what you do is go down looking for 0.2. That's on the values on the vertical axis. You find 0.2. Well, you're looking for 0.21 specifically. So you start to go horizontally from the 0.2 that you have marked down. Here it gives you 0.20. If you look up, is it 0, 0.01, 0.02, 0.03 on the horizontal axis. So here on the vertical axis, we have 0.2. So we start to move horizontally. Here it gives us this probability at 0.20. Then we move on to the next one. Here it gives us the probability at 0.21. 0.2 plus 0.01 gives you 0.21. If the z-score was 0.23, this won't stop here. We'll continue to move further. This gives us 0.22. Then we go here 0.23. But this score in our example is 0.21. So we first start with the vertical. We go down 0.2, then move horizontally to find the two decimal placed value 0.20, 0.21. And here we have it. The probability of values, the percentage of the probability of values falling below the z-score of 0.21 is 0.5832. So we round off to 4 decimal places of 58.32%. And that's why we described there that by observing the table, we determine that for a z-score of 0.21, probability of z less than 0.21 is equal to 0.5832. But if we want to find the values that lie above the z-score of 0.21, then we use our complementary probability concept. So we do 1 minus the probability of z lower than 0.21 to get us the probability of z greater than 0.21. So that will be 1 minus 0.5832, which is equal to 0.4168. All of this being rounded off to 4 decimal places. There are negative and positive z-tables. This one we illustrated here is a positive z-table. These tables can be found online with a simple Google search. I will look at some examples to understand their use in the succeeding slides. Note that an alternative to the z-table is the z-score probability converter, which can also be found online by a simple Google search. Z-score probability converter. You can find many examples of automated ones on the internet. But for this module, focus will be on the use of z-tables. So now we look at, now to look at some examples. Yes, the first one, suppose temperature readings are normally distributed with mean equals 0 degrees and standard deviation at 1 degree. This should help us in that this is a standard normal distribution. Find the probabilities that a randomly selected temperature reading agrees with each of the following. A, less than minus 1.5 degree, B, less than 1.23 degree, and C, greater than 2.22 degree. So the solution is, we can observe that this is a standard normal distribution. Hence, the temperature readings are the z-scores. So we go through to determine the probabilities from the z-table. If following the standard normal distribution, we have to first compute the z-scores based on the mean and standard deviation. But this question is already a standard normal distribution. So we just, whatever the values are already the z-scores, and we just go to the z-table. Notice that the first one, A, we say less than minus 1.5 degrees. We use the negative z-table. To find the probability that we have a z-score less than minus 1.5, the answer is 0.0668 or 6.68%. Those are the values to the left of minus 1.5 degrees or lower than minus 1.5 degrees. To find the probability of this was less than 1.23 degrees, we use the positive z-table, since this is a positive value. Using the z-table, which I'm sure you must have found online, we get a value of 0.89 0.07. Now, if you use the positive table, you will first use the vertical axis to search for 1. From 1, then you look at the decimal places on the result to get 0.23. That will give you 0.8907 or 89.07%. Now, to find z-score greater than two values greater than 2.22 degrees, that means our z will be greater than 2.22. The z table does not compute probabilities for those values greater than the z-score. It only computes for less than. So we have to first find the values that are less than 2.22 degrees and then subtract it from 1 to get those that are greater than 2.22. So for z less than 2.22, we get 0.9686. And then to compute probability for z greater than 2.22, we have 1 minus 0.9868, which gives us 0.0132 or 1.32% probability. I'm sure that has improved our knowledge of using the z-table. I'm sure you follow through it. The z-table at hand or online. Now, the second example. The length of human pregnancies from conception to death approximates a normal distribution with a mean of 266 days and a standard deviation of 16 days. What proportion of all pregnancies will last between 240 and 270 days? That's roughly between 8 and 9 months. Here we can understand that our mean is 266 and our standard deviation is equal to 60. This is not a standard normal distribution. So we have to compute the z-scores. I know z-score equals to x minus the mean over standard deviation. So at 240 days, the z will be 240 minus 266 over 16. X in this case is 240. The mean is 266 and standard deviation is 16. So we get minus 1.625. While at 270 days, to compute the z-score, it will be 270 minus 266 divided by 16, giving us a z-score of 0.25. And the probability of pregnancies, proportion of pregnancies falling between 240 and 270 days. And we are finding the probability of z-scores falling between minus 1.63 and 0.235. That's greater than by 1.63, but lesser than 0.25. And that will mean find the probability of z-scores lesser than 0.25 minus find the probability of z-scores lesser than minus 1.63, as we can see here. Using the z tables, P with z less, probability of z less than 0.25 is 0.5987, while probability of z less than minus 1.63 is 0.0516. So we subtract the values and we get from there we get 0.5471 and we followed through this example of 54.71%. Now in 54.71% of all pregnancies will last between 240 and 270 days. That's the second example. Hope that's clearly understood. We can pause and go through it over and over to understand the intuition behind the example. And the third example, the average resting heart rate of an adult is 65 heartbeats per minute. If the standard deviation of the population is 5 beats per minute, determine the proportion of adults with a resting heart rate above 75 beats per minute or BPM. You can see that the average resting heart rate is 65 BPM, which is giving us a mean of 65. And the standard deviation of 5, as the standard deviation of the population is 5 beats per minute. So mean is 65, and standard deviation is 5. This is also a normal distribution, so we have to compute the z-score. We are looking for the proportion of adults with a resting heart rate above 75 beats per minute. So our x in this case is 75. So complete the z-score with x at 75. We give us 75 and 65 divided by 5, giving us a z-score of 2. So at 75 BPM, the z-score is 2. We want a probability that we're finding x greater than 75 in terms of finding probability of z greater than 2. Z greater than 2 is equal to 1 minus probability of z less than 2. Using our positive z table, a probability of z less than 2 will give us 0.9773. Hence, the probability of a z-score greater than 2 will be 1 minus 0.9773 or 0.0227 or 2.27%. Therefore, 2.27% of adults have a resting heart rate above 75 beats per minute. All those examples are clearly understood. So with those examples understood, we look at some exercises. So there are 2 here I would like you to look at. The first exercise, we're interested in knowing how likely it is for one type of tree to grow to a certain length. The length of these trees exhibits a normal distribution. The tree that you measure is 120 centimeters, 120 cm. Given the following information, do you think this tree length is uncommon for this type of tree? We have a mean tree length of 100 centimeters and a standard deviation of 10 centimeters. And then the second exercise, the height of adult females are normally distributed with mean 1 centimeter and standard deviation of 8 centimeters. Find the probability that a randomly selected adult female has a greater height than 170 centimeters. So these are the exercises. We'll give about 5 minutes to go to try and solve them. Don't be in a rush. Understand the questions and then solve them. So you have 5 minutes. Yeah, 3 minutes left. We have less than a minute, about 45 seconds. 45 seconds. Okay, that's time is up. So we look at the solutions to the exercises. That's the solution to question 1. Looking at the question, we can see that the mean is 100 centimeters and standard deviation is 10 centimeters as stated here. And now our x in this instance is 120 centimeters. We're trying to find how common the tree length of 120 centimeters is. So we have to compute the z-score of 120 centimeters. That will be 120 minus mean 100 divided by 10, the standard deviation, which will give you a z-score of 2. This means that the tree length of 1 centimeter is 2 standard deviations above the mean. Using a positive z table, we have to find the values of the probability of finding a value which is less than 120 centimeter, or find the probability of a z-score less than 2. So find the probability of a z-score less than 2 is equal to 0.977 using our positive z table, 0.977 or 97.7%. What that means is that 97.73% of these species of tree under consideration are shorter than 120 centimeters. Hence, the probability of finding a tree 120 centimeters or greater in length is 2.3%. Therefore, trees of this type, 120 centimeters in length, are relatively uncommon. We don't find them that often because 97.7% of trees are shorter than 120 centimeters according to our calculations and the use of the Z table. Very straightforward to calculate. Now, the solution to question 2. We find here that the mean is 160 centimeters and the standard deviation is 8. And as I said, we want to find the probability the probability that a randomly selected adult female has a height greater than 170 centimeters. In this case, x is 170. So we compute this score again. The z-score as 170 centimeters is 170 minus 160, which is the mean, divided by the standard deviation of 8, which gives us a z-score of 1.25. Now, I want to find the probability that we can get when we select a adult female, should be above 170 centimeters. So P, probability of X greater than 170, which is same thing as probability of Z greater than 1.25. These are complementary probability concept. If I find the probability of Z less than 1.25, then subtract it from 1 to find the probability of Z greater than 1.25. That overall will give us 1 minus 0.8944. 1 minus 0.8944, and that will give us 0.1057 or 10.57%. So the probability of randomly selecting an adult female who will have a height greater than 170 centimeters is 10.5%. If you didn't get this answer correctly, nothing to worry about. Just more practice and maybe going back to better understand the formula and the use of the Z tables. Practice makes perfect as always. You can always try to get a better understanding of these calculations. Now, with the exercise done with, we summarize our module. So the next on the agenda is the summary. What are the key takeaways from this module on normal distribution? The first key point, we discussed normal distribution characteristics. What are those characteristics? Let's recap them. The distribution is symmetric about the mean. That means half of our values fall below the mean and half of the values fall above the mean. The mean, median, and mode are all equal. And then the empirical rule or the 68, 95, 99.7 rule, I'm sure you're quite familiar with it now, tells you where most of your values lie in the normal distribution. 68% occur within one deviation of the mean, 95% within 2 deviations, and 99.7% within 3 deviations of the mean. That is the 68, 95, 99.7 rule, or the empirical rule. The second key point, the standard normal distribution, also called the Z distribution, is a special normal distribution where the mean is 0 and the standard deviation is 1. It is a form of normal distribution in which the variables have been standardized. Here you know that standardization involves using the Z-score formula, where your individual data point X is subtracted from by the mean and then divided by standard deviation. And I'm sure we can easily tell when the distribution is standard, normal, or when it's just the normal distribution. Once we see that our mean is 0 and our standard deviation is 1, we can automatically tell that this is the standard normal distribution. And then there will be no need to compute for these scores because those scores become automatically Z scores. Now, the third key point, these scores tell you how many standard deviations away from the mean each value lies. This value is the formula to determine this score value is Z equals X minus the mean over standard deviation. I'm sure we are very, very familiar with this formula now. So the Z score tells you how many standard deviations away from the mean each value lies. So if you compute for X, compute the Z score for X, and we get a Z score of 1.3. That tells you that that X is 1.3 standard deviations away from the mean. If you compute the Z-score computed is 2.5, that tells you it's 2.5 deviations away from the mean. That's the importance of the Z-score in normal distribution. Now, the additional references to get a better and a deeper understanding of normal distribution. Here on mathworld.wolfram.com, Eric Weinstein developed normal distribution, developed a material on normal distribution. There we can find mathworld.wolfram.com. And then Leon in 2014 published Why Are Normal Distributions Normal in the British Journal for the Philosophy of Science. So we said there are many references for us to go through to get a better and a deep understanding of normal distribution. So if after going through this module you want more knowledge, you can go through these materials of these references. The title of these published works are available here, the author, the year, and even the journal on which they were published. So that will be all on the normal distribution. Thank you very much, and I hope this has better granted you an understanding of the normal distribution. Thank you.